Hey everyone, I'm Michael Hall, and you're watching Innovation Coffee, brought to you by ARM, where we give you a deep dive into the ARM developer ecosystem with special guests and topics that bring you the latest innovations happening on ARM. This episode, we've got Kunal Pathak from Microsoft, who's here to talk about the latest .NET release, version 9, and the improvements that have been made to that using ARM's SVE instruction sets. Then we've got our ARM ambassador, Konstantinos, who most of you know by now. He's showing off the latest work that his company, VectorCamp, has done around SIMD.info, their new website to show off how to migrate code to use ARM's SIMD instruction sets. Finally, we're going to get our update on learning paths. This time, Joe Stech will be joining us again for that. Kunal, welcome back to our show. How are you doing?
I'm doing good. How about you?
Doing great. Now, the last time we had you on an Innovation Coffee episode, you were telling us about the introduction, or the integration rather, of SIMD instructions into, it must have been .NET 8 at that
Mm-hmm.
point.
Yep.
Now, .NET 9 is out, and you've introduced the scalable vector extensions from ARM into that.
Yep.
And you have a presentation that you want to share with us about that. So I'll go ahead and just hand it over to you to start that.
Okay. Yep. Hi everyone. For those who don't know me, I'm Kunal Pathak. I'm working in .NET JIT team and working on this past release. We were working on the scalable vector extension support in .NET 9. So let me just give an overview of like what we did in .NET 9. Um, so we added like around 281 new APIs to expose the non-streaming SVE intrinsic support, and the APIs were ranging from bitwise, math calculation, counting, load store, and things like that. We added around 1100, more than 1100 instructions, new instructions encoding for the non-streaming SVE version 1 and version 2. And right now, since this is like really in early stages, we have it enabled just for vector length 128 bits, but in future releases we want to make it like vector length agnostic, the way SV has basically. I have also published a very detailed blog post of about the engineering SV in our .NET. So I would advise for people who are interested, go through it and let us know your feedback or any questions. Just for primer, like the SV 101, basically the SV stands for Scalable Vector Extension, and it lets you give a scalable size to the vectors. So if you see in the orange, you already had the SIMD vectors, which are 16 bytes long, but now with SVE you can also have vectors that are greater than that size, up to I think 2048 bits, and each vendor would decide like how much vector length they want to incorporate in the chip. So that gives us like you write a software once, and then whenever you deploy it on multiple different vendors' hardware, it will take advantage of the whatever the vector length is, and you can see the performance boost without even having to change your code. It also introduces a bunch of like predicate registers. There are 16 predicate registers, and that gives a new concept of a programming model where you can do a predicated manipulation of the lanes. So if you are like if you have 16 lanes of 16 lanes in the vector, and you want to just operate on few of them, you can like turn them on or off based on those contents of the predicate registers. Um, so what we did was we have a vector T data type in .NET already, which was meant to be used for this purpose, where if you have a variable length vector, we represent that using vector T. And we reuse that vector T for our scalable, for the SV implementation. We use that for representing both vector and predicate values. We don't have a separate data type for predicate values. And I will give you examples like why that worked out for our situation. But it let us it let us express some of the unpredicated, predicated only, like different variants of this instructions that SV introduces, just by using the vector T data type. Just to give a quick like examples, to I want to give two examples here. One is there is a instruction called ABS, which calculates the absolute value of the source operand. And if you see at the bottom, like the instruction takes PGM, which is basically a predicate register, and predicate register tells like only this many lanes needs to be calculated for absolute value, for the others do not touch. So what we did in .NET 9 is like we expose this ABS API, and that just takes one operand and it doesn't take the predicate operand. And I'll show you like how we were able to generate this predicate operand or predicate register content just by taking this one source operand. So what we did was we just wrapped the ABS, the method call into a conditional select, something called conditional select. And what that does is it just manifests the predicate value to be all true. So what it says is all the lanes needs to be calculated, and for the true value, so it will calculate all the absolute value for all the lanes. And since here there are no inactive lanes, the third operand that you see here, that will not be used. So basically we are achieving the same parity that the instruction meant to have. So just by like doing this wrapping in the JIT itself, we able to accomplish the instruction's purpose. Let's imagine somebody wrote a code something like this where they want to actually use conditional select, and where they say like all the just give me the value of this operation, the result of this operation only for the active lanes of the mask, and don't, and for the inactive lanes just use the merge value. And we were able to like identify that pattern, and then based on that we basically like streamline that to produce the code with the predicate register variants, as you see on the screen. And again, like all these details are I've explained it in much more details in the blog post, so would advise to like just go over it. There is another example that I wanted to show is there is an add instruction which has both the predicated as well as unpredicated variants. The predicated variant is similar to the ABS example that we have seen in the previous slide, where it takes the predicate register, but the unpredicated variant doesn't take any predicate register. It just operates on the entire on the two source operands, like all the lanes of the source operands. Even for this variant, we just expose one set of API which takes just the source vector register and the source vector value and the two source vector values. Now, if we see a user or developer has typed SVE add, we know that they want to use unpredicated variant. So we just detect that pattern and we generate the code of the unpredicated variant of the add instruction. However, if we see that there is a the developer has used conditional select, that means they want to use the predicated version of the add instruction. So we detected that pattern, and depending on the register contains and the destination registers and whatnot, we generate the code with the predicated variant. So for example, here you see there were the registers were different, so we generated the unpredicated version, but then we use the SEL instruction, which is essentially the conditional select instruction, to actually pick the contents from the appropriate lanes. On the right hand side, since the destination registers were same, we just try to emit the predicated version of the add instruction. um just to quickly call out that since there were like so many instructions and so many APIs to be implemented in like really short time span in the .NET 9, we tried to auto generate bunch of these things. And what we did was we took the ARM manuals, which are in like XML format, and we just parsed them and generated all the boilerplate code that we needed. And whenever we were implementing like adding this encodings, we were just like copy pasting those logic that the tool had generated, and that actually speed up our development cycle like very dramatically. So for encoding instructions, like we generated around 16,000 lines of code, which the developer just like copy pasted, did minor changes, and the encoding was done. Similarly for APIs, there were like 24,000 lines of code that we just auto generated, and then while implementing we had to copy paste it and just test it and got it going. So that was like I think like one of the key contributor to our fast development in the .NET 9. Want to take a brief moment on like what we are trying to do in the future releases. As I said, the vector length is right now just 128 bits, and we want to make it like truly scalable. So all the code that we generate, we want to make sure that it understands or it knows, it can figure out the vector length from the hardware, and then depending on that, like generate the code. So no matter on 256 bits or 512 bits, it should just work. We also want to light up the vector t with the SV intrinsic. So imagine like you have two operands of vector t, and you are doing addition operation. If you are running this code on the SV hardware, SV supported hardware, then we want to actually just generate the scalable variant of this add operation instead of the neon variant. We still have to do a bunch of work of supporting the ahead of time compilation scenarios, like native AOT and cross-gen, and that will give developers a way to compile all this into native AOT and then port on different type of hardwares which has different vector lengths without doing any changes to their code base. There are since this is like a V1 of our offering, there are like a lot of code quality improvements that we have to do. There is like diagnostics and debugging support, like how can we see the scalable registers contents while debugging? Are the predicate registers content be visible? So we have to still add those things. And lastly, and most importantly, is we want to take a step forward and do the design and implementation of the streaming mode SVE and SME going forward. So I think, yeah, that's our long term plan, and it might take easily like one or two or three releases to achieve like the end to end SVE feature on .NET 9. Thank you.
Thank you for that great update, Kunal. It's always amazing to see the work that's going into .NET to keeping it on, the very latest feature set that ARM has, so that it runs as fast as possible. Especially now with the new Cobalt processors that Microsoft has developed for Azure, those are becoming available now, so people can, run these AI and machine learning workloads even faster on those
Mhm.
because of these optimizations. So,
Yep.
once again, thank you for being on the show. Thank you for this update. We'll put a link to your blog post in the video description, so anybody who wants to dig deeper into that, you can go ahead and check that out. Otherwise, you can just start using .NET 9 on this new ARM hardware and take advantage of it. Isn't that right, Kunal?
Yeah, yeah, because the Cobalt hardware that you mentioned, like that does have SV feature enabled. So yeah.
All right, so go check that out. Kunal,
Mhm.
thanks again, and we'll see you for the next .NET update.
Sure. Thank you.
Take care.
Thank you, Michael. Bye.
All right, next we're going to go to Konstantinos to see what his company's been working on with SIMD.info. Konstantinos, George, welcome to the show. How are you two doing?
We're doing great. Thank you for the invite. It's a pleasure.
All right, now anybody who's been in the ARM community for any amount of time knows Konstantinos. You're always active in our Discord, you've been on our office hours, and for months now you have been hinting at this project that VectorCamp has been working on. So I'm really excited that you've come on the show today to show that off to us. Um, and also kind of give us a backstory of how it came about. So I'm just going to hand it over to you, Konstantinos, to tell us about SIMD.info.
Thank you, Michael. So I'm going to start with a small story. Many years ago, I wanted, I'm crazy about, you could say I'm a fanatic about CMD optimizations in general. I mean, uh, with every architecture, not just ARM, because I think that it's a way to make your computers run more efficiently. And I mean, it's there. Why not use it? I mean, why let it go to waste? So the story was I wanted to make it easier for programmers like myself or anyone else, basically, to be able to write and port code from one architecture to the other easily. I mean, because for anyone that has done this work for more than a simple exercise, you really have to read a lot of documentation. I mean, we're talking about thousands of pages. And I want to have a single resource that would be available to everyone. So that started as a book in 2015. I wanted to write a book, and there was actually an Indiegogo campaign, something like Kickstarter. And believe it or not, ARM was actually a sponsor at the time, even. And unfortunately, it didn't go very well. But the problem was the size of it. I completely underestimated the size of the whole thing, the whole venture. I wrote about 100 pages of LaTeX, and I didn't even finish addition. So it was clear that this is not the way. This is not really a book material. It would go to thousands of pages, and I would probably be finished with that probably after my retirement. So yeah, I need to rethink about this. So it was put in the backlog for a few years, and right around 2020, when we started our own company, uh, it started to become a bit more clear on what I wanted to do with this, and turn it into an online resource. And then the AI craze was starting to become very popular, and everyone was talking about AI. So, okay, why not build an AI that does this stuff and produce all the information that we want automatically? And we actually did that. And we did a demo, internal demo to to some people, including some ARM people. And it was promising, but there was not enough data. I mean, that's the whole problem with AI. You need to have the data. So we said, okay, we cannot obviously scan the whole internet because it's still not going to be enough. So we need to provide our own data. And what's the best way to provide the data than provide an online knowledge base with the data itself in a readable form, so that other developers can use and find the information they want, but also we can use that as the basis for an AI model. But we need to first write the data. So after a couple of 3 years, well, 2 years, 2.5 years of doing the work more or less alone, at some point we got some new people and in the team in VectorCamp, and George was one of them, and he started immediately to work on this project. And I have to publicly admit that his contribution was exceptional. He has done amazing work, and it's really I'm saying some things, and George immediately understands what I need. But let's not spend too much time on the history and start actually look at the project itself. So the company is currently comprised by 4 people. We're a small team. So it's Krisa. She's the CEO. I'm the CMD guy. And George is a CMD developer. Also, you're another George. He's also CMD developer. So it's we hope to grow the team, but for now it's good. Right. So what is the CMD? CMD is an extension. Is a set of extra instructions that are used to perform some optimizations, some operations in a more efficient manner. It doesn't really make your computer go faster, but it allows your computer to execute the same instruction or more data. So you can do an addition on 4 or 8 or 16 integers, depending on the data type and the operation involved. And it has about a 20 years history. It started with Intel, with MMX, sorry, and then a power gave the birth to the Altivec extension. For those people that remember the G-Force in the old Power Max, and then ARM came with Neon, and every architecture has its own set. Over time, this grew up to become a very complicated superset of set of instructions, and for those instructions, you have the equivalent C intrinsics, which are a way to call these instructions, these assembly instructions, from within a C. So most of the developers don't write assembly; they write the equivalent C code using those intrinsics. And you have 7,000 intrinsics for Intel, 7,000 intrinsics for ARM, and I mean, RISC-V is a complete disaster. It's like 20,000 intrinsics. You cannot learn this stuff. It's impossible. And you have newcomers like the long-swim Chinese ones and etc. So let's just agree that it's a complete, it's a very complicated issue. You cannot learn this stuff. So this is the problem. You have the instructions. You need to use it. Otherwise, what's the point? It's like having a car and using only one cylinder, right? What's the point of having more if you're not going to use them? And all these instructions are complicated. You need to have someone that knows this stuff. And most of the time, these are part of very complicated and long instruction set manuals of thousands of pages long. Let's meet the actual project. SIMD.info. As I said, it's an online resource of all the major SIMD architectures. And it started as a book, as we mentioned. So for now, we have covered most of Intel intrinsics, most of ARM. We haven't covered SVE yet and SVE2. But the plan is to pretty much include everything. I mean, if it's SIMD architecture, we're going to try to include it there.
All right, so this is SIMD.info itself, and this site is live now, right?
Yes, exactly. And as you can see, it's pretty bare, pretty simple, which is on purpose. We wanted something really simple and light that developers can use without any distractions. I mean, no boxes or ads or anything. We just want to have the information available at all times. So let's start from the top menu. You can see there is a search bar, and there is also the intrinsics tree, which is the one of the most powerful features. So imagine if you could categorize all of the instructions in the intrinsics in a completely human-readable manner. So let's go to arithmetic, for example. Let's pick something simple like vector add. And you have multiple cases of vector add. Let's go with, I don't know, 32-bit floats. I mean, it's very simple, something that everyone's using. And you have the AVX2, Neon, SSE, and VSX. If you click on an intrinsic, let's click on the VAddQ, for example, which is the ARM Neon one, you will see that the ARM Neon, you have the intrinsic name, you have a link to official documentation, you have the description, the header that it's included, what kind of result, and the actual prototype. But this is not all. I mean, if you want, you can click on the full description, and you can check that you have the intrinsic. You have an example of how to use the intrinsic. So this is this is one of the plans to have an example. You can copy it directly to your code, to your editor, and start playing around with it, do some experimentation, see how it works. And you're looking at the tags, and you will see they discuss on below. And this is okay. We thought that it would be nice to have something like a Stack Overflow for a particular instruction. You want to ask a question for this particular instruction. You don't want to ask a generic question. You want to ask something very particular about this. Hey, I'm trying to do this, but when I'm using this input, it gives me something completely, I don't know, unintuitive. Something I cannot understand. Why is that? So, first of all, you will get an answer. But second, and most importantly, other people who will be looking at this same instruction, they're going to see that remark, that response, and they will be able to reply, add their comment, or maybe even start a debate. Oh yeah, no, this is not the right instruction to use. Let's go and use another one, or stuff like that. So something like Stack Overflow.
Now people can form a community around sharing their knowledge in these SIMD instructions and help each other out.
Exactly. All this experience, it's out there, but it's very distributed. So we really want to start in adding some diagrams. I mean, this is a work in progress, but adding diagrams for 17,000 instructions is not going to be easy. I mean, it's not 17,000 yet, but if we add SVE2 in that, yeah, it's going to go 17,000 easily. So you see all the number of SIMD intrinsics currently available, and that's a lot of information. But you are also going to look. Maybe you're also going to note that there are some equivalents. So let's say I'm working on Neon, but I want to port this instruction to another architecture, or vice versa. I'm working on SSE4, and I want to see what the equivalent for Neon is. Let's go and click on the equivalents SSE4 too. So it gives you what other intrinsics are there tagged for the same operation on SSE 4.2. And you click on that, and you see, okay, I have this intrinsic. Let's click on that. So you see exactly the same. And you get that operation. And this way you are able to navigate across pretty much all intrinsics on every architecture and get the information that you want. You can get all the prototypes. I mean, what kind of data type does it use? Is it a M188 or it's a float 32 times 4? Stuff like that. So you can look at the actual prototypes. You can look at the actual code. And in the example, this is something we're working on. We haven't added it yet. We want to show the actual output of the example. So when you execute that, what kind of code, what kind of output are you going to expect? What is the result of the print? And so, which is sometimes you don't have the hardware or the time to take the code, compile it, and run it and see the output. You just want to know what's the output is going to be. So we're going to do that also. But there's a cool feature that I really like, and it's the comparison. So you want, let's say, okay, we have this instruction, auto comparison. Let's click on that, and let's go to I don't know, VSX. So you have the power. You can add that to compare. Just add to compare, and also go back to Neon. So let's add this one and add to compare. So we have added 3 intrinsics in the comparison. Let's go to the comparison, see how it's going to open a new window with all the 3 intrinsics that we have added and their difference. So this is really cool. I mean, as a SIMD developer, this is something I always wanted. I mean, I had to read 3,000 pages in the ARM manual, another 3,000 pages in the Intel manual, and about 1,500 pages in the IBM manual when I wanted to see the equivalent instructions. And when you start adding more instruction sets, it's going to become even larger. So having something to quickly compare the intrinsics, that's a time saver.
Yeah, this is great for people who are just starting out. Putting optimized instructions in their code, they can see how to support multiple architectures from the beginning. Or if they've already done this, they already have those Intel optimizations in there. They can just say, "I know I'm using this. What's the ARM equivalent of it?" And that's going to make that process so much easier.
Exactly.
And you're going to look and you're going to note that there are some links on top next to the architecture name, full intrinsic, and the view official documentation. We don't want to copy or duplicate the information that is added on the Intel or ARM website. So for more information, if someone wants to really look at the details like cycles of the instruction, or what register, what kind of latency changes in between architecture revisions, we don't want to include that information. This is left for the CPU vendor. So you can click on the view official documentation for the VAD queue, for example, for ARM, and it will open a new window straight to the ARM Intrinsics website, and you can just expand on VAD, and you can see all the extra information that you want. I mean, it's not going to replace all those websites. It's going to complement them and bring them together. I mean, I understand completely that ARM is not going to work on something to improve Intel documentation and vice versa. but you still need that kind of binding on how it maps, or how each intrinsic maps together to the other. Another thing that we want to add, I mean, this is the intrinsics tree. We're working on the instructions tree. So for assembly level coders, we're going to do the same thing, but for the assembly level. So just the assembly instructions.
Okay.
And of course, we also have the search bar. So let's say you want to look for the proper FMA instruction, and let's say we're not interested in the VSX. We just want to know the FMA instructions for ARM. Yeah, so you have VFMA, F64, and this is one of the instruction to do a fused multiply accumulate. This is what FMA stands for. Actually, there are two. This is the first version, and there is the VMLA also. But in essence, you are able to see how it's supposed to be used also. You have the operations, you have the example code, you are able to copy and paste and try it, and you have the prototype description below. And if you want to ask something, yeah, go ahead. So, yeah, we also have seen the equivalent intrinsics. So we already described. That's a good point. The tag. So let's say you want to see how many other instructions are there that do this operation. If you click on the tag, then it will give you a list of all the intrinsics on every architecture that are tagged with this particular operation. So you see currently all the operations there. You see also the VMLAQ, which is the newer instruction. Now this is very, very, very interesting, because when you know the operation that you want to implement, let's say you have the C code, and you want to implement the function in a separate architecture, in different architectures, and you know the operation. The operation is multiply accumulate, and these are the intrinsics that you are going to be interested in. So the tagging is also a very interesting way to look at and search for intrinsics. Now, as we said, this was the whole point of that, is to do a CMD, an AI model, to be able to try to translate code from one architecture to the other. And you're going to notice a link there, SIMD.ai. What is that? Does it
I
work?
did see that up there, yeah.
Yeah, so this is a mock-up, but we're working on the actual stuff right now. So let's say that you want to translate this particular code, which is a very simple function. It doesn't really do anything clever, but it was just a demo to see how it can work. And you click on translate. And you're going to wait for a while, and voila, you have your code in Neon.
Wow.
It's a mock-up. It doesn't really work right now.
But it's in
But
progress.
it's in progress. We actually, as I... with George, and the other George, we're currently testing 27 LLMs, popular and not so popular, some generic and some code-centric, that are really focused on generating code.
Mm-hmm.
And we are testing them on how well they can be used to translate and learn from our data set, to translate code from SSE to Neon, but also not... Basically, we want to do it for every pair. But obviously, the most important example is going to be from SSE to Neon, because that's what legacy developers are going to be using to transfer their code base from old existing instances, VMs, or physical hardware, to modern ARM hardware, or even Windows software. I mean, Windows on ARM is now playing a very important role, and a lot of code there is hard coded for x86, and these developers are going to want to port that code to ARM. So this is definitely going to help them. So the idea is to have all the pairs involved, and you're going to be able to select the pair, the source architecture, the target architecture, and maybe we would like to allow also the choice of the model. Maybe some models are better suited for a particular code base. Some other models might be more suited for the opposite, the reverse operation. We don't know yet. We don't know, but we're going to allow the possibility.
That is an exciting possibility, and we will have you back on again to show that off once that is live.
Yeah, happily. Yeah, we will definitely do it.
All right. But for right now, people can go to SIMD.info today and check out what we've been showing off already. That is live. It says it's in beta, but
it is in beta,
everything
but
that
yeah,
you've seen
it should be usable. Yes.
Yes.
awesome. All right. And then we will put a link to Konstantinos' full slide deck in the description of the video below. Once again, Konstantinos, George, thank you so much for being on the show. Thank you for showing this awesome tool off that you've been working on. And yeah, keep us updated as things progress so that we can get you back on again.
Thank you, Michael. Thank you. It has been a pleasure.
All right.
Thank
Take care,
you.
y'all.
Thank you for listening. Yeah.
All right. Now let's wrap up the show the way we always do with an update of our latest learning paths. For that, we're going to go to Avon and Joe.
Hey, everybody. I'm here with Joe to talk about some new learning paths that have just been released.
Thanks, Avon. October was another month full of releases for learning paths. I'm going to focus on 3 topics today: GitHub runners, Google Cloud's new Axion processors, and some generative AI topics. First up here is MLOps on ARM-hosted GitHub runners. ARM actually just won the GitHub Technology Partner of the Year award at GitHub Universe. We've been very happy with our collaboration with them. This particular learning path is all about creating a more complex GitHub Actions flow for MLOps. And you'll go ahead and set up an ARM-hosted GitHub runner, train a PyTorch ML model, and then containerize everything and automate those steps in an ML workflow. This is a really a little bit more in-depth application of GitHub runners than we've done before, and we're pretty excited about this. So check that out. The next set of things I want to talk about are learning paths related to Google Axion processors. So Google just recently released these to general availability. We were very excited about that. And we've actually got 3 different Google Axion processor learning paths. The first one is related to Java on Axion. And just at a very high level, what you'll learn with this one is to create an ARM-based VM instance with a Google Axion CPU, and then go ahead and deploy a Java application, and then learn a little bit about performance tuning on Axion. And if you have an existing x86 application that you'd like to run on Axion, this is a learning path you might want to check out. So this learning path will teach you about adding ARM-based nodes to an existing x86-based GKE cluster. And overall, this will just help you learn how to run a multi-arch application across multiple architectures on that single GKE cluster. And then with respect to incorporating Axion into all parts of your stack, we've got a CI/CD pipeline learning path that will allow you to use GitLab on Google Axion. It's actually possible to create GitLab self-hosted runners with Google Axion instances, and this learning path will help guide you through that. So now I'm going to switch gears a little bit and talk about some generative AI topics. This is a great learning path that we built in collaboration with Zillas. Zillas creates the Milvis vector database. It's actually one of the most popular open source vector databases. And I've used it for clusters, for a vector database cluster that had over 100 million embeddings inside the cluster. You can do very quick Euclidean distance calculations with many, many embeddings using Milvis. And this particular learning path explains how to use Zillas Cloud, but you can also use self-hosted Milvis with this particular learning path. And then the final thing I want to mention here is that we've updated our Llama, Clyde AI, Executorch, and XNN pack learning path. The updates are mostly around the Llama 3.2 release, but other than that, everything is very similar in this learning path. We've just updated it to work with Llama 3.2, and that's it for me.
Awesome. All of those sound really, really interesting. I know I personally am going to go through all of them. Thank you so much, Joe, for telling about these new learning paths.
That's our show, everybody. Thank you for sticking around, and make sure that you subscribe to our YouTube channel so that you get the latest videos as we put them out. We will see you all next time.